So now we basically move out of the realm of what you can find in books and on the internet, and now we have a look at what happens when things go wrong in real life, and how do we identify the effect that we see? How do we identify what's causing it? And in some cases, how do we help? How do we fix it? Okay, so this part is going to go into the process effects that we see in our lithography process, and it's also going to showcase some of these using real-life pictures from the clean room. What I want to show you here is I've made some drawings that are supposed to represent looking from the top on the resist and also the cross-section. And what we are looking at is the resist patterns where the design is a fairly large square. So several tens of microns in size. And I'm going to look at the effects of what kind of exposure mode we use, so proximity or contact. Also look at the exposure dose, so overexposure, underexposure, and the development time, underdevelopment, overdevelopment. And we're going to start with the positive tone resist, and then we're going to repeat everything for the negative tone resist to see a little bit about the differences between the two. And then there is some real-life images again. So what I have here is an example that shows bright field design. So we have a square which is filled in the center. So the chrome would be the black here. And then you can see down here in the cross section, you can see the chrome layer on top of the resist. And then we can see for a positive tone, we get a nice square, and we get nice square profiles as well. And for the negative tone, we get a square hole. And you can see that I'm sort of, for the negative tone, I'm already expecting in the normal case the negative sidewalls. So that means we are looking at a resist which is like our Enlof negative resist that always has the negative sidewalls. All right. So first, let's look at the positive tone resist. So in this case, we are looking at the two cases, the bright field design and the dark field design. So in one case, we have a chrome square, and in the other case, we have a square hole in a chrome film. And you can see there the result. So this is the normal expected. So this is the contact case is supposed to represent the ideal case where everything is right? So we have perfect contact, we have the perfect dose and the perfect development. And then let's have a look at what happens when we look at proximity. So in this case, we move from perfect contact and then to a not perfect contact. So there is a couple of microns of gap between the two here. And keep in mind, this is exaggerated, right? This is to show that the effect, it's not to scale of what you would see on an actual 20 or 30 by 30 micron structure. But the effect that we get in the positive tone resist is that when we look on the top of the resist, we can see that the air gap that we have introduced actually makes the light that comes from the perfect square in the mask diffract. So what happens is that we get exposure on the, well, actually underneath the chrome, you can see here, right? So the square becomes smaller. And you can see that the effect is sort of double in the corner, because you have something diffracting from one side and something diffracting from the other side, and they superimpose in the corner and gives you a double effect. But then you can also see, if you look below, at what happens what happens in the cross section. So you can see we get a smaller square on the top, but it actually becomes a bigger square on the bottom. And this is because when the light diffracts, it effectively spreads out the energy over a larger area. So as we move down through the resist, the effective dose is lowered, which means that it doesn't dissolve as much in the developer, so we get this positive sidewall in this case. And if we look at the case in the dark field design, you can see again the light sort of bleeds out underneath the chrome, and you can see that the effect is actually reduced in the corners in this case because it points away from the corners. And you can see the same slope, again the same positive sidewall angle in the cross section. So again, with the proximity here, we get funny corners. We get a smaller size on the top of the resist, but a bigger footprint. Okay, so now let's look at the exposure dose. So now we are going back in perfect contact, and now we're just checking the case where the dose is too low or the dose is too high. So in the case of the underexposed here, in the extreme case, of course, we get the problem that it's not fully developed. So when we keep the development time the same, then when the dose is low, maybe the dissolution rate in the bottom half of or maybe in the overall resist layer is lower. So it takes longer time, but when the development time is fixed, that means it doesn't have time to go all the way through. And what you can also see is the effect of, even though we are in perfect contact, there is still a little bit of diffraction. So there is a little bit that sort of is lost all around the edges. So the entire structure becomes a little bit bigger. But you can see that, so we have on the top view, we have a bigger square, but the corners look nice. And you can also see a slight effect that as we go down through, we probably have a slight positive sidewall angle, because when we are not really exposing enough, then we start to see the effect that the dose is actually higher on top than it is on the bottom. So we see this positive slope there. And it's kind of reversed when we reverse the polarity of the image. So we get a slightly smaller square, and we still get this layer on the bottom and the positive sidewall again. So if we go to the case of the overexposed, then you can see that we start to get something that looks a bit like the proximity. So what we are seeing is the diffraction again, and the diffraction is causing the light to go below the chrome pattern, and it's also causing this double effect in the corner. But you can see that because we are still exposing a long time, so we are actually we are overexposing, so we are fully exposed all the way down, and there's plenty of time for all of the resist to bleach, so the sidewall is still nice. So you can see slightly smaller structures, truncated corners, but still straight sidewalls. And then when we look at the dark field design, slightly larger hole, but still straight sidewalls. Yeah? Let me know if you have any questions. Okay, so now let's look at the development time. So again, perfect contact, perfect exposure dose, and now we just develop shorter or longer than the optimal case. So if we don't develop long enough, we get the effect that something is left on the bottom. So we have thin layer of resist between our structures. But the structure itself is actually reasonably perfect because the dose is correct. So we get the right size and we get the right sidewall angle. And the same here for the dark field. So the hole is the correct size. We may be left with a little bit of resist on the bottom. If we develop for too long, we start to see the effect of dark erosion. So it first develops all the way down like normal, and we have the perfect size. But now it then starts to eat away at the sides and on the top because of the excess development time. So we get a slight reduction in the size and also in the height of the structure. And the same is repeated here, so that translates into a slightly larger hole and again slightly thinner film. Okay? So now we've been through, well, this is basically sort of the exaggerated theoretical effect of all of the things that we can vary in the process. So let's have a look now at a real life process. So this is a process flow for a positive tone resist. It's the 5214E resist, coated to around 1.5 micron. And then I go to the aligner. Use the hard contact, of course, except for when I use the proximity. And I use the exposure dose here, listed here, except for when I reduced it or increased it to see the effect of over and under exposure. And the same goes down here in the development, 60-second development, except for when I increased or decreased it to see the effect. And then finally, I'm having a look at some line and dot patterns, both in the bright field and dark field design. And I'm using a 20 times magnification objective in the microscope. So this is first what the design looks like. So this is the mask. The top is the bright field design and the dark field design below. And this is the size of the structures. So we have three lines of similar size and the same spacing, 4 micron on top and 1 micron on the bottom. And then on the side there is squares, holes or dots of the same dimensions. So if we start by looking now at the exposure mode, so this is contact versus proximity. So if I have contact exposure, so this is hard contact, you can see that we get almost perfect resolution here. So in this case we have, we can, it's difficult to see. The resolution of the optical microscope is around 1 micron anyway, so it's difficult for us to really figure out whether the 1 micron lines are resolved or not, but they seem to be there. There is something there. They are probably not the correct size and they may not be fully resolved, but there is something there. And the 4 micron lines look really perfect, as you can see. So now the question is, what happens now if I purposefully introduce a 2 micron proximity gap? So I did another exposure, told the machine to use proximity exposure, 2 micron gap, and the result is this. So there is several things going on here. If you start by concentrating on the bigger lines, so the 4 micron lines on the top or on the very bottom here, you can see that the lines, they look rather nice. And then you can see as we go down in size, things start to go completely wrong, right? So there's a couple of effects that are nice here. So I think I wanted to point, yeah. So you can see, like around here, can you see how the square pattern has suddenly rotated 90 degrees in angle? So instead of having 4 dots like this, we have 4 dots like that instead. And this is typical for a proximity problem, because this is basically near field diffraction. So this is what happens when you look at the diffraction pattern very close to what generates the image. And you can see the smaller ones, they completely disappear. And the bigger ones, they just have some funny corner effects, and some of them are rounded or something like that. But other than that, the big ones are not affected so much. So what we see with the proximity effect here, so in this case, I'm using a proximity gap which is sort of comparable to the thickness of the film. So this is something that would be typical for a mask that has maybe picked up some film on previous prints, and then we get this gap on our print. And you can see that if we were doing 5 or 10 micron structures, we probably wouldn't notice. But if you're going down below 2 micron, then you really start to see the effect. Okay, so now let's look at, so I mean, with the exposure mode, this is really either something that we choose or that we cannot control, right? We cannot control the dirty mask. So in some cases, this is not something we can control. But the rest of it, exposure time, well, the exposure dose and the development time, this is something we can control. So now let's look at here where we vary these two and have a look at how much can we vary them without seeing a big effect, which gives us an idea about how sensitive we are to the exposure dose and to the development time. So I should have maybe introduced first that this time we are only looking at the bright field design again. So the mask is there in the first picture, and then below this is what the optimal case is. So this is what we are comparing to, right? And then I reduced the exposure dose by 20%, and you can see immediately we have a problem, because there is actually resist film left in the gap between the structures. So this wouldn't work. We wouldn't be able to transfer the pattern, because if we tried to do an edge, then there would still be resist that would inhibit the edge, so it wouldn't work. But if we go to the other direction and say, let's increase the exposure dose by 20%, you can see that they're very similar. It seems like the smallest dots have been lost. So they're starting to go away. And if I increase even further, this is sort of seems to be the same again, right? That the smallest dots are disappearing, but the lines are actually staying there, right? So this is probably something that has to do with how big the footprint is. So when you have a dot, then it sort of goes completely away sooner than if you have a long line, because it has a lot of, it has a bigger area to adhere to the substrate. But you can see if we were looking at, when we look at the 4 micron lines, it's still perfect even at a 50% overexposure. Well, relatively perfect, right? And if we were using this to produce structures that were 10, 20, 100 micron, we wouldn't see it at all. So then let's try to see what happens if we then underdevelop. So we go back to the correct dose, but then we just cut the development time in half. And you can see this has a similar effect to the underexposure. This really destroys our process. This doesn't work. So let's try to go in the other direction and develop basically for twice as long. And you can see this has a similar effect to the overexposure. The smallest structures are lost because they're completely dissolved. But the lines, they still look pretty okay, and the big structures, they look really fine. So in this case, you can see that we are sensitive to underexposure and underdevelopment, which means that when we do the exposure, it's better to expose for a little bit too long and develop for a little bit too long than the other one, because then we are insensitive to small variations. You know, there could be temperature variations of the developer bath, or there could be slight variations in the intensity of the exposure light. So if we already know that we are a little bit above to begin with, then we will not see problems in our daily work. Another thing that we can also use these, that I tried to use these to measure, was the dark erosion. So I tried to see what is the difference in the height of the structure when I compare the optimal case to the one that has been developed for twice as long, because that would be what I would think was one of the problems, was that the film was actually eaten away. But in this case, the dark erosion was actually smaller than what I could register with the method that I used for measuring the thickness. So in this case, below 10 nanometers in a 1.5 micron film. So very little dark erosion. So again, it also means that we shouldn't fear the development. And it also means that if we have one day a case where we see the underexposure, we can maybe fix it by just developing twice as long. Because that would maybe take care of the very thin film on the bottom, but it wouldn't harm our structures. So.